Welcome to This Explainer. Today, we're unpacking the elegant mathematical theory behind OrbSwap's polar coordinate architecture and, well, contrasting it with the messy, undocumented realities of its on-chain engineering. It's a really fascinating look at what actually happens when pristine academic math collides with the rigid, unforgiving constraints of smart contracts, and more importantly, why that collision directly matters to your wallet.
All right, so here is our roadmap for today. We'll start off with the polar AMM theory, hit the hardware determinism wall, uncover the precision and granularity blind spot, look at some ambiguous gas and ticks, and finally do a little digital archaeology by digging into the commits. Let's get right into it.
Section 1. The polar AMM theory. We have to start by understanding the beautiful, high-dimensional math that the OrbSwap research paper promises. So, by anchoring the coordinate system to a focal point, the protocol uses trigonometric conversions to shift liquidity. Think about it like this. Instead of just sliding up and down an x and y axis like older traditional models, it rotates. This creates these massive, capital-efficient, n-dimensional superellipses. Mathematically, it's absolutely stunning.
On paper, the theoretical ideal is a seamless geometric dream. You've got these perfectly smooth curves dictating exactly how one asset trades for another, completely bypassing traditional Cartesian limitations. The theory essentially promises that if you use angles and radii to represent price and liquidity, you can achieve incredibly tight slippage for stablecoins that trade near a 1-to-1 ratio. Sounds great, right?
Well, that brings us to Section 2, the hardware determinism wall. Because here is where that pristine blueprint crashes headfirst into concrete reality.
As you can see here, off-chain math relies on hardware approximations, what researchers sometimes jokingly call the FPU wood chipper. Systems like Google's TurboQuant can use floating-point math to do complex polar coordinate geometry because they run off-chain for AI, where a tiny rounding error, totally fine, no big deal. But in decentralized finance, determinism is absolute law. Literally, every node on the network must compute the exact same result down to the decimal. That requires rigid, absolute, integer-based fixed-point math.
So, to survive on-chain, those continuous flowing curves of polar coordinates must be forcefully translated into strict fixed-point math. Now, the authors of the OrbSwap paper actually acknowledge this in a brief remark, admitting that floating-point math just can't be trusted on-chain. But, acknowledging a problem and actually documenting its solution, those are two very, very different things.
Which leads us straight into Section 3, the precision and granularity blind spot. This forced translation creates a massive gap in the academic research.
Check this out. The official paper actually provides a code snippet using standard 64-bit floating-point variables, specifically F64 in Rust, to compute the sines and cosines for their swap function.
But here is the massive ambiguity. The exact bits of precision used for production are just completely missing from the research. The Ethereum virtual machine, and by extension, the Arbitrum stylus environment they're deploying on, does not natively support these floating-point trigonometric functions. So how exactly do 64-bit floats scale up to 256-bit integers? The white paper basically shrugs and doesn't say.
Without knowing the exact scaling factors, this is a real problem. When you compute a sine or cosine using integer math, you literally have to round off the result. In a high-leverage decentralized exchange, a rounding error isn't just a quirky math problem, it's a financial discrepancy. A few way off here and there really compounds, meaning users can lose money. And the paper totally obscures the mechanics of how these fixed-point conversions are actually handled.
And that bleeds directly into our next part, Section 4, ambiguous gas and ticks. Because every piece of complex math on the blockchain comes with a literal price tag. Look at these missing variables. The paper acknowledges that if all assets are priced at exactly $1, the neutral polar tick sits at 45 degrees, ranging anywhere from 0 to 90 degrees. But it completely fails to define the exact angular tick granularity. Are the ticks spaced 1 degree apart? A tiny fraction of a degree? It also casually skips over the heavy gas realities of those scale multipliers.
Let's be real, doing heavy trigonometry on-chain fundamentally alters the cost to the user. Calculating a square root or trying to simulate a sine wave using a Taylor series approximation, that burns a massive amount of gas. Every single arithmetic step costs money. Plus, if that exact tick spacing we talked about is too fine, crossing multiple ticks during a volatile market swing could cause your transaction cost to absolutely skyrocket.
Section 5. Digging into the commits.
Since the white paper leaves us totally in the dark on these massive engineering realities, we basically have to become digital archaeologists.
To find the actual truth of how this works, an auditor has to toss out the pristine academic PDF and literally dig through raw GitHub commit history. The sheer glamour of crypto research, right? You literally have to hunt through the Arbitrum stylus Rust code just to see how they translated that theoretical 64-bit float into something the blockchain can actually digest.
And when you dig deep enough, you eventually discover that the real backbone of the system is not that 64-bit float example at all. No, instead, it relies heavily on highly specific hard-coded EVM integer scaling libraries hidden deep within the code. Libraries like PRB Math. They use WAD scaling, multiplying values by 10 to the 18th power just to mimic decimals. This PRB Math implementation, along with those hard-coded constants, is the heavy lifting that actually keeps the pools invariant intact.
Ultimately, the actual implementation fundamentally shifts the protocol from a theoretical ideal into a very gritty engineering compromise. It's a brilliant compromise, for sure, allowing for supra-elliptical stablecoin pools on-chain, but it absolutely requires accepting round-off errors and massive mathematical overhead that the research papers would rather hide behind smooth, perfect curves. I'm going to leave you to chew on that provocative thought. Are we blinding ourselves to the true mechanics of these systems by focusing too much on the academic theory and not enough on the messy, hard-coded reality? Thank you so much for joining me for this explainer. Keep exploring, stay curious, and I'll catch you next time.